Hi.
Yes, good morning to all. So today, let us
Good
discuss.
morning, sir.
Yes, good morning. So today we are going to discuss about the factors affecting on the IR vibrational frequency. Last time we are discussing about the effect of hydrogen bonding. Factors affecting on IR vibration frequency. So there in that one we are discussing about the hydrogen bonding. IR spectroscopy. So here we have learned last time that suppose you are having carboxylic group. Here is R, C, double bond O, O and H. The second molecule of carboxylic group, here is OH, C, double bond O and R. So between these two molecules, there is a presence of hydrogen bonding, and you are getting such type of hydrogen bonding. It undergo dimerization because it form bond between the two molecule. So here is the partial negative, partial positive, partial negative, partial positive. Similarly, we can write such type of polarization in the COOH group. As the H positive is nearer to the O negative, there is a formation of hydrogen bonding. So here there is a formation of such type of H bonding. Now, how this hydrogen bonding will affect on the vibrational frequency? So, if there is a presence of OH, where there is a presence of hydrogen bonding, presence of H bonding, H bonded, then in that case, due to the H bonded stretching frequency, there is a presence of a band at 2700 to 2500 centimeter inverse. So remember this point. We have learned already that when there is a presence of OH, either maybe COH or maybe any other alcohol and phenol, if H, here is a no H bonding, in that case we can say that if there is a no hydrogen bonding, in that case it will appear near about at 3550 centimeter inverse. You have learned this point. But suppose if there is a hydrogen bonding, this OH will be shifted towards 2700 to 2500. Right? Means it will affect on the hydrogen bonding. So as there is a presence of hydrogen bonding between the two molecules, so it is a intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Okay. Now, if you take another example, for example, suppose if there is a benzoic acid, para-hydroxy benzoic acid. So here we can write another example like this one. HO, here is a benzene nucleus, presence of pi bond. Here is a C double bond O. OH. Then another molecule of para-hydroxy benzoic acid, we can write like this one. Presence of pi bond, and here also C double bond O and OH. So look here, here is a partial negative, partial positive. Here is a partial negative and partial positive. So between these two molecules, also there is a formation of a such type of hydrogen bonding. So it is example of intramolecular hydrogen bonding. Between the two molecules, intramolecular H bonding, right? H bonding. So if you take the spectra, you will see that here the OH actually should appear at 3550, but it will appear at 2700 to 2500. Okay, but on dilution means when you add more and more solvent, if you take more dilute solution, then what happens? The OH stretching which appear previously at 2700 to 2500 centimeter inverse, it will shift to 3550 centimeter inverse. So this effect of on dilution. So what happens? The solvent will go inside these two compound, and the OH of the two compound, they'll go away from each other. That's why what happens? There is no hydrogen bonding. So on dilution, no hydrogen bonding. That's why there is shifting of such type of compound takes place. Okay, so it is example of intramolecular hydrogen bonding. Again, suppose if you take the another example, for example, if you take the same hydroxy benzoic acid, but here the COH group, C double bond O, and here is the H, and here is O, and here is the H. In this case, here is a partial negative, partial positive, again partial negative, partial positive. There is a formation of a such type of hydrogen bonding, and this hydrogen bonding is called as intra. Intra means within a molecule. Intramolecular H bonding. Intramolecular H bonding. So this intramolecular hydrogen bonding here will be appear the band that you get in this case is the CO will appear at 1665 centimeter inverse. At the same time, the OH band will be appear at, that is, we can say here, as there is a hydrogen bonding, in that case, as there is a hydrogen bonding, in that case, you may say that it will appear at 2700 to 2500 centimeter inverse. Okay. So what happens? In the presence of intramolecular hydrogen bonding, CO will appear at 1665 and the OH will appear at 2700 to 2500 due to the hydrogen bonding. But suppose on dilution, right? On dilution, what happens? On dilution means if you add more and more solvent. So here there is no effect on vibration frequency. No effect on vibration frequency. We get the same vibration frequency due to OH and CO. Then question arises, why it do not undergo shifting? Because here it is a single molecule. As it is a single molecule, even though it on dilution, the intramolecular hydrogen bonding will remain as it is. But in the previous example, on dilution, what happened? The two molecules, they will go away from each other. These two molecules, they will go away from each other. And here there is a free hydrogen bonding. That's why here, if you see, the CO of this compound appear at 1678 centimeter inverse, and the hydrogen bonding will appear near about again 2700 to 2500. But on dilution, what happen? The two compound, they will go away from each other. RC double bond O, here is OH, and there is a solvent, right? There is a solvent, and the two compounds, they will go away from each other, and there is the absence of hydrogen bonding. So there is no H bonding. As there is no H bonding, then the COH, in this case, the CO will be appear, the CO here, the CO will be appear at 1760 centimeter inverse, and the OH will be appear at 3550 centimeter inverse. In the previous case, here the CO will appear at 1678, and on dilution it will appear at 1768, means there is again the shifting towards the left side, right? So that's why here there is effect of hydrogen bonding on the vibrational frequency. So such type of hydrogen bonding will present in a different compound. For example, there is a presence of hydrogen bonding in alcohol, ROH. Here is O, here is R. So again, there is a presence of such type of hydrogen bonding. And why? Because there is a partial negative and partial positive charge, partial negative, partial positive, partial negative and partial positive. So here is the presence of intermolecular hydrogen bonding in alcohol. If there is a phenol, suppose if I write such type of R, and that is your phenol, here also O, H, and also H, O, and here is phenol. Pi bond, pi bond, pi bond. Again, here is a partial negative, partial positive, partial positive, partial negative. So there is a formation of a such type of hydrogen bonding. So due to the H bonding, right? Due to the H bonding, the frequency will be appear at lower. Okay. This is the example of intermolecular hydrogen bonding. Also, there is a formation of intramolecular hydrogen bonding. Just now I have taken one example, orthohydroxybenzoic acid, that is a sulfuric acid. Again, suppose if you take such type of example, CS2, here is O, here is H, here is O, and here is H, means 1,2-diol. So here also there is a formation of hydrogen bonding, partial negative, partial positive, partial positive, partial negative. Okay, and again in amines and amides also there is the presence of also hydrogen bonding. So in amine and amide, amine and amide, amine and amide. So what happened here? There is in dental you can write R, N, H. Here is H, right? Then here is N. Here is H, H. Or you can write here R, and here is H, right? So what happened here? Partial negative, partial positive. Here also partial negative and partial positive. So there is a formation of hydrogen bonding. So as there is a presence of two NH bond, so it can form hydrogen bonding with these two hydrogen. If suppose if it is a primary amine, it is your primary amine. Similarly, secondary amine R, N, H, R, also it can form hydrogen bonding. But if there is a tertiary amine, then there is an absence of hydrogen bonding. So it is a tertiary amine. Similarly, we can write amide also. Amide, here is R, C, double bond O, N, H2, H, H. It may also form hydrogen bonding. So this effect of hydrogen bonding on the vibrational frequency. So due to the hydrogen bonding, what happened? The length of bond get increased, means it gives the single bond character. As it gives the single bond character, the bond length get increased, force constant get decreased. So the vibration frequency get decreased, means it will appear towards the right side. Okay. So this about the, that is the effect of hydrogen bonding. Next example, if you see the steric effect also affect on the vibrational frequency. Steric effect. Steric effect. More the crowding, in that case, how it affect on the vibrational frequency. For example, suppose if you are having, that is the vibrational frequency of a cyclic ketone, vibrational frequency of cyclic ketone, cyclic ketone. For example, here is a cyclohexanone, double bond O, then cyclopropanone, then cyclobutanone, cyclopropanone. So here you are having cyclohexanone, similarly you can write other examples. Cyclohexanone will be appear, the CO stretching will be appear at here 1710 centimeter inverse. Cyclopentanone will appear at 1740 centimeter inverse. Similarly, the cyclobutanone will be appear at 1775 centimeter inverse, and this one will appear at 1818 centimeter inverse. Okay. So as we move from cyclohexanone to cyclopropanone, so as we move from cyclohexanone to cyclopropanone, means when the size of ring get decreased. So here there is an increase in the steric hindrance. The angle strain here get increase, and angle strength get increase, and in that case it is observed that the vibrational frequency also get increase. So remember this one. So as the size of ring get decrease, the angle strength get increase, the vibrational frequency also get a increase. Okay, so this is about the here cyclic compound. So it is depends upon the angle strain, right? Another example we can take here, that is the, suppose you are having CH2 double bond CH, C double bond O, and here is a CH3, right? Then CH2 double bond CH, C double bond O, then CH double bond CH2. Similarly, CH2 double bond CH, C double bond O, and here is a H. If you see this compound, here is a methyl vinyl ketone, here is a divinyl ketone, and here is a this compound vinyl carbaldehyde. So this will appear at 1705, then 1670, and here it will appear at 1685, right? So here you find that pi bond open on the oxygen, this pi bond they are involved into delocalization. Similarly, pi bond open on the oxygen, this pi bond will be involved into the delocalization. So as the conjugation get increased, here there is a methyl and vinyl, it appear at 1685. Then there is a vinyl and vinyl, it appear at 1670, and this will appear at 1705. So as if you compare the two compound, suppose for example if I write 1, then 2, and then 3, suppose if I take 1 and 2, here there are presence of two pi bond, they are involved into delocalization. So there is a presence of such type of structure, CH double bond CO minus, and here is a CH double bond CH2. Similarly, also the pi bond may be also involved into delocalization, means you are getting one more structure. But here in the first structure only you are having one resonating structure, and it gives the single bond character. But here there is also presence of conjugation, but there is a hydrogen, there is absence of, that is the R group. So if you compare structure number, for example 2 and 3, in 2 and 3, as there is a presence of the two vinyl group, they exhibit plus R effect, it gives single bond character, and as compared to 3, only there is a presence of only one pi bond, it gives a single bond character. So here more the single bond character, less is the vibrational frequency, means the compound number 2 it appear at 1670, and compound number 3 will appear at 1705. If you compare compound number 1 and 2, again similarly you will find that here there is the presence of two pi bonds, they are involved into delocalization, it gives a single bond character, but at the same time in the first compound only one pi bond, they are involved into delocalization, so it gives the single bond character. So more the delocalization, more the single bond character, more the single bond character, less is the force constant and less is the vibrational frequency, so it appear at 1670. Okay, so in this way you can also compare like this one. So more the conjugation, then in that case more the resonating structure, so it will lower the stretching frequency. Again, if you take the another example like this one, suppose if you take a benzaldehyde, this is your benzaldehyde, here is a pi bond and pi bond, there is the presence of C double bond O and H, it is called as a benzaldehyde. It will appear at 1700 centimeter inverse. Another example here, if I replace the hydrogen by the methyl group C double bond O and CH3, that C double bond O and CH3, it will appear at 1690. And here, if there is a presence of, that is double bond O, and here also there is a benzene nucleus, okay, and it will appear at 1670 centimeter inverse. Okay, so these are the vibration frequency. So here in the first example, you will see that there is a, in all example the pH is common, the phenyl nucleus is common, right? But as we move from left to right, you will see that there is an increase in the methyl group, and this methyl group, there is a more crowding. As there is a more crowding, it will appear at the frequency here 1690, and again there is a presence of two benzene nucleus, so again there is a more crowding, it again appear at a lower 1670. So here you see that as there is a presence of more crowding, the more steric hindrance lower the vibrational frequency, it lower the vibration frequency. So more the steric hindrance, less is the vibrational frequency. We can see in this way also. Okay. Similarly, we can take the another example. For example, suppose you are having the carboxylic acid. You are having the carboxylic acid, that is the R, C double bond O, here is the O and H. As the pi bond, they are involved into delocalization, the lone pair on the oxygen, they are involved into delocalization. So you are getting single bond character, right? You are getting a single bond character. The lone pair on the oxygen, they are involved into delocalization. So here this will appear at, the CO will be appear at 1720 centimeter inverse. Okay. Now if I take the example like this one, the R group exhibit plus I effect, at the same time the lone pair on the oxygen, it exhibit plus R effect, so it gives the single bond character. So plus R, and in this case there is a plus, at the same time also the oxygen also exhibit minus I effect, also minus I effect, right? But plus R effect is more powerful than this minus I effect. That's why you are having the stretching at 1720. Suppose if you take the such type of example, here is a benzoic acid, presence of pi bond, right? Or we can take, here is a C double bond O and OH, right? If you take corresponding analog, cyclohexanone carboxylic acid, double bond O and OH. Okay, so it is seen that this will be appear at 1725, then it will appear at 1700, and again if I write the another example. Here there is a pi bond, pi bond, pi bond. Here is a CH double bond CH, and again C double bond O and OH. So it appear at the CO appear at 1680 centimeter inverse. So centimeter inverse is the unit of the wave number. Now you will see that in the first example, cyclohexane carbolic acid, second example benzoic acid, and third example is your, that is the increase in the conjugation. So alpha beta unsaturated carbolic acid called as a cinnamic acid. So in first example only there is the presence of, that is the plus I effect. Here there is a plus R effect. Here there is more increase in the plus R effect, right? So more the plus R effect, more the conjugation, more the single bond character, more the single bond character, less is the force constant. That's why less is the vibrational frequency. That's why the third compound appear at 1680, second compound appear at 1700, and the first compound appear at 1725. Book to book this value may be also different. Okay. The next example, this example of acids. If you take the ester RC double bond O, here is the O and R. There is the presence of the two lone pair. So here the R group exhibit plus R effect. It exhibit plus I effect. Okay. At the same time, the lone pair on the oxygen also they are involved into delocalization, and this R also exhibit, that is the plus I effect. So of course it undergo resonance, and again you are having such type of resonating structure. Okay, so here there is a plus R. The esters will be appear at 1740 centimeter inverse, and the esters will appear at 1740 centimeter inverse. So ester, we have a combination of the plus R effect of lone pair and minus I effect of oxygen. So I result is esters normally show the carbonyl stretching at 1740 higher than the carboxylic acid. If you compare the ester, the esters will be appear at higher than that of the acids. So here, if you compare the acids and the esters will appear at higher frequency than the acid. Okay, so this about the called as the vibrational frequency of ester. If you take the another example, that is acid halide. Acid halides are RC double bond O. Here is, we can take halogen, for example chlorine. For example, we can take the example chlorine. So here we see that the CO will be appear at 1790 centimeter inverse. At the same time, when there is a fluorine, it appear at 1850 centimeter inverse. So acyl chloride and here acyl chloride. So chlorides appear at higher than the first compound. Why? What is the reason? The reason is that the chlorine exhibit a powerful minus I effect as compared to the chlorine. So the length of the CO get decreased as compared to acyl chloride. That's why more the force constant and more is the vibrational frequency. So if you compare, then we have to write like this one. Okay. At the same time, if you take the another example of carbonyl compound, that is the amide. Amides are having the functional group RC double bond O NS2. It is your amide, right? In amide, there is a presence of plus I effect. At the same time, the lone pair on the nitrogen, they are involved into the delocalization, means it gives the single bond character, and you are having such type of resonating structure. Here is O negative, C positive, double bond N S2 and positive. So the amides will be appear here. The plus R is powerful than the minus I, right? So it will appear at 1,6. The CO will be appear at here 1,690 centimeter inverse, means lower. Why? Because there is a plus R effect. Here there is a plus R effect. The lone pair on the nitrogen, they are involved into delocalization. That's why it gives the single bond character. More the single bond character, in that case the force constant get decreased, vibrational frequency also get decreased. Okay, so these about the amide. Now these are some functional group we have taken their vibrational frequency. Okay, so the last point, that is the important point in every spectroscopy, that is the application of IR spectroscopy. Application of IR scopy. IR spectroscopy. Of course, one common for all, to determine the structure of a molecule. To determine structure of molecule. To determine the structure of molecule. So here in every spectroscopy, UV, IR, NMR, we will see that it is useful to find out the structure of organic compound. So it gives idea about how to find out the structure of molecule. So under this point, we can write one, we can find out in the functional group region. It is useful to find out the functional group. We can take any, that is the band. For example, suppose if there is a presence of a spectra at in between 4,000 to that is a 3,000. So if there is a oxygen, you may say that there is the presence of OH. If there is nitrogen, there is the presence of NH, SH, or even though if suppose there is a presence of pi bond, then you can say there is a presence of a CH stitching of a double bond, then triple bond, or maybe of benzene nucleus, right? So getting a band in a particular region, or presence of a band in a particular region, it gives an idea about the presence of the functional group. Even though if there is a carbon-carbon triple bond, it appears at 2100. Carbon-carbon double bond, it appears at 1600. If there is a carbon-carbon single bond, it appears at 1100. Right? So here, getting a particular band in a particular region, you may say that there is a presence of so and so functional group, right? And if suppose there is a presence of a peak in the aromatic region, then you may say that there is a presence of, that is the aromatic compound. So functional group will give the idea about the functional group. Then fingerprint region, it used for the to compare the sample. So here no two different molecules have the identical IR spectra. So this region is useful to give the idea that whether the compound they are same or different. They are the same or the different. So for the sample comparison, we can find out the fingerprint region. And we have seen the aromatic region. Aromatic region, just now you have seen, you can write any bands that you know. So first is to find out the structure of molecule. Number two, here to study the progress of chemical reaction, right? So by using this one, we can study the progress of chemical reaction. Progress of chemical reaction. We have seen that we use a TLC. We use a TLC to find out the progress of reaction. But here also the IR also gives idea about the progress of reaction. How? If suppose you are having a such type of a reaction, if there is a, here is a OH, here is a H, and it undergo oxidation, and after chemical reaction you are having corresponding product, that is the cyclohexanone. If you take the IR, you'll see that there is the presence of OH. So this OH generally it will appear at here 33002 3500 centimeter inverse, or you can say about 3000. So you are getting such type of important band about 3000. But if it undergo oxidation, so there is a removal of hydrogen and there is a formation of ketone, and the vibrational will be appear at 1700 centimeter inverse. So there is a change in the band. So in the previous case it was at 3300, but in the second case in the product we are having a band at 1700, and there is absence of the previous band. Means here we can say that we can monitor the rate of reaction, we can monitor the progress of the reaction. Okay, the third example, we can detect the hydrogen bonding, right? Can find out the detection of H bonding. Detection of H bonding. How we can find out the H bonding? Just now we have learned the number of example. Suppose you are having alcohol ROH, also ROH. So due to the presence of the hydrogen bonding, here the band in this one, it will appear near about at somewhat, that is 32000 to 3500 centimeter inverse. But so there is a presence of intermolecular H bonding, but on dilution, here on dilution means when you add solvent, then what happen, the ROH will go maximum away from each other, right? And here there is a solvent, right? There is a solvent, so there is an absence of hydrogen bonding, so there is no bonding, no H bonding, right? And if you take a spectra, you will see that this will be shifted towards the left side, means at a higher, and it will appear near about at 36000 to 3650 centimeter inverse. Okay, so in this way we can find out whether there is a presence of hydrogen bonding or whether there is a presence of protic or aprotic compound. So it is useful for the detection of the hydrogen bonding. Okay, so even we can find out whether there is a presence of inter or intramolecular hydrogen bonding. So in intermolecular hydrogen bonding, it changes its vibrational frequency, but in case of here is intra means within the molecule, there is no effect on the vibrational frequency, even on the dilution, right? And next one, number 4, we can find out the size of ring. So whether you are having a 6-member ring or 4-member ring or a 5-member ring like this one, we can find out the size of ring. Just now we have taken this example, right? So here it is a 6-member, then here it is a 4-member and 3-member. So as we move from left to right, then angle strain get increase then vibrational frequency also get increase. So here we have said that it will appear at 1710, it appear at 1740, then 1775 and 1818. Okay, so the it use the idea about the size of ring. And the last application, detection of impurity, right? The number 5 example is the detection of impurity. Detection of impurity. So this IR also gives information whether there is a presence of impurity or not. For example, suppose you are having a compound that is, for example, ketone, that is acetone, right? Suppose the pure compound is your acetone, right? So as it is acetone, so the CO will be appear at 1710 centimeter inverse or near about at 1700. But suppose if there is a impurity present of alcohol, for example, if there is a presence of ethyl alcohol, right, ETOH, ethyl alcohol, if there is a presence of ethyl alcohol, right, so here CS3, CS2 and OH. So here with this 1710, suppose there is impurity, then the OH stitching will be appear at 3500 to 3200 centimeter inverse. If suppose there is impurity of a benzene, if there is a impurity of benzene, here you know the benzene, there is a CS stitching will be appear, the CS stitching will be appear at 3100 centimeter inverse. At the same time, carbon-carbon double bond stitching will be appear at 1600 to 1500 centimeter inverse. So we can take any compound and we can say that another impurity is present. So presence of that band in that compound, you may say that impurity is present, or we can detect the presence of impurity. So here this point is very important. The application of IR spectroscopy, the first application that is common for all, that is the determine the structure of molecule. Under this you can write any point that you know to find out the functional group region, fingerprint region and the aromatic region. So you can write the use of these three: fingerprint, functional group and the aromatic. Second is the progress of chemical reaction. Just like a TLC, if you take the spectra of the reactant and the product, the spectra will be different. So the alcohol OH will be appear at 33 and CO appear at 1700. Detection of hydrogen bonding. If there is a presence of inter or intra, we can detect by using the hydrogen bonding. So on dilution, it will shift towards the left side, means at higher frequency. And we can find out the size of ring. As there is a decrease in the size of ring, the angle strength get increased, the vibration frequency get decreased. Then detection of the impurity. If you take a compound, a pure compound, for example, if it's a acetone and if it contains the impurity of ethyl alcohol, so with 1710 you may also get the spectra of OH at 35 to 3200. If suppose there is impurity of benzene, then you may also get spectra. The CS stitching of a benzene, it appear at 3100, which is absent in the acetone, and carbon-carbon double bond you may appear at 16 to 1500. So in this way we can find out the detection of impurity. So these are some of the points about the application of IR spectroscopy. Okay, so in this way we have completed this topic. If you have any doubt, you may ask. Yes, may I audible? Hello? Okay. So So here we have completed this topic, and the next part is very important, that we have to go on the numerical. If you understand the theory behind this one, you will see that there is no need to read theory. You can solve all the numericals. You have to give some revision on the numerical data where it appear. We have seen some points where it may appear, function group, then fingerprint, and the aromatic, right? And accordingly we have to solve the problem. So I will take one of the example from each type, and you have to solve yourself the remaining example. Okay, so here we have to stop this IR spectroscopy. Okay, thanks to you.